Alright, we got some more computational differential equations coming your way. And what we're doing is we're finding a polynomial of degree 3 which interpolates sine at these points. We get 0, pi over 6, pi over 4, pi over 3, and then plot this polynomial against sine on this interval from 0 to pi over 2 and see how it looks. See if it makes sense. Okay, so you define these functions. Well, basically the points, we want to know the not only what the xi values are, but we want to know the points on this, whatever this function, so this is u of x. Then we want to know this capital U1 and this capital U2. So defining the capital U's will give us, like, they'll allow us to find these actual points on the graph of this function. Of course, this graph that I've drawn doesn't really make sense here because the function we're approximating is sine, so it would really look like that, but better and not awful. But anyways, the point is we want to define capital U0 through capital U3 to be sine evaluated at these xi values. And then we want to find a polynomial such that evaluating it at xi I will give us capital Ui, meaning that p of xi I will be the same as sine of xi I, because those are the points that we want it to equal at. So then we use the Lagrange polynomials, and our formula is p equals this sum thing here. And this is the one thing about this problem that might annoy some people, is that there's a lot of computations that you want to do here. Not too bad, but it's quite a bit. So basically, if you take this and you expand it out, it looks like this, and then you just plug all the values in, and then you just reduce it a little bit. And you reduce it some more, and basically you collect all the degree 3 terms, you collect all the degree 2 terms, collect all the degree 1 terms, and then there's no degree 0 terms, it turns out. Which makes sense because sine, when you evaluate sine at 0, you get 0. So if you had a degree 1 term, then it wouldn't match up at 0. And xi 0 equals 0, so you want it to, even though it can be a little bit off at some points, it has to be equal at these 4 points. And in particular, it has to be the same at 0. But anyway, so now let's plot it. And this is cool because we can plot it and we can actually see if this works. And it looks like it does. This looks like a really good approximation. So let's see here. What points were we looking at before? We wanted 0, pi over 6, pi over 4, pi over 3. So 0, what is pi over, what are these numbers? So let me pull out my calculator really quick because I don't know these numbers off the top of my head. So I don't really know numbers that well. So pi over 6 is about a half, a little over a half. So let's take a half here. Right, and I chose this grid point. Like, I'm not showing you what actual code I used to make this in MATLAB, but I chose the code such that for 0, pi over 6, pi over 3, and pi over 4, for all those values, they actually coincide with some of these points. Like, for each xi I, there exists a point in this grid which is equal to xi I. That's what I mean. Okay, so pi over 4 is about 0.78, so it's going to be somewhere around here. Yep, that seems to agree there. And then the last one is pi over 3. That's about 1.04. Perfect. Yeah, so if we look at these 4 points, it's like pretty much right on the dot there. So this is a really good approximation, it seems. And also notice that the one region where it seems like it's a little bit off is this region out here, and it kind of makes sense because this is like the 4 points that we're using to interpolate are way over here, and so once you start getting away from where all those points are concentrated, that's when you start getting into the region where they differ a little bit. But yeah, that's about it. So not only have we constructed a polynomial of degree 3, which we're trying to use to approximate sine, but we can actually see what's happening, and we can actually see if we're doing a good job. And we see that we are doing a good job. So this isn't like in this is one thing that I like about like numerics, is that you can plot these pictures, and so you can actually use the pictures to see very concretely if you're on the right track. It doesn't guarantee that you're completely correct, but it at least shows you that you're on the right track. Whereas in some abstract proofs, like proofs in abstract algebra or in analysis, or pretty much any pure math proof, it's not always obvious. Like there could be like a logical gap between 2 points, and it's really subtle, and you don't quite catch it. But there's not always a way to like verify that, or to indicate that you're on the right track. But here we do have something concrete that shows us that, well, yeah, it agrees here, 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 and here. And you can actually go into what I used to plot this, and you would actually see that it actually gives you the exact correct value. But yeah, that's about it for this problem. We've done everything that we wanted.